for the most rest of you. Um, I'm Terry Alger, and today I'll be talking to you about simulation for thermal runaway and battery safety assurance. Um, this is just a little bit about myself. I'm the currently the Vice President of Innovation and Applied R&D for UL Solutions. I lead a team of scientists developing physics-based safety solutions across multiple disciplines. Um, I've been doing this for a while now, working on batteries since about 2010 or so. So the objective of this presentation is to show how you can integrate modeling simulation and then thorough validation of those models with testing to transform the approach from battery safety assurance from more of a reactive kind of a testing environment to a proactive standards-aligned methodology that really takes advantage of some of the advanced predictive capabilities that are out there. Um, and on the right-hand side, you can see the agenda. I do have a short intro to UL Solutions for those of you that aren't familiar with our company. We'll talk a little bit about why thermal runaway still is a problem, um, review the risk landscape and standards, and then look at a couple case studies that we have, and then kind of close it up. And I will try to leave plenty of time at the end for questions and discussion, if we should have it. Okay, so for those of you that aren't familiar with UL Solutions, we are a global product TIC organization. So we do testing, inspection, and certification of a variety of products that range everywhere from industrial components and systems through consumer goods and electronics. From the battery standpoint, we've got 6 laboratories located mostly near automotive R&D hubs that serve battery storage, innovation activities, and product development. Our company itself has about 15,000 employees in 140 locations. And you can see on this map that we are fairly geographically diverse. Oops. Our battery facilities, our major one is in Auburn Hills, Michigan, and also in Chengdu, China, with another facility in South Korea. Our R&D team is located in Taiwan, and we've got another R&D and product development group in Germany with some modeling people in Spain. So we're a global organization that represents battery development, all over the world. So we've got quite a bit of experience in battery testing. Our standards are involved in certifying batteries for safety and are called out in several uh, electrical codes and fire codes worldwide. We've got a pretty broad team of engineers that are engaged in safety science. So enough about us. Maybe we'll talk a little bit about why this is an important topic. And when I talk to people about batteries, it's interesting in that the battery has been around for a while, and you'd think by this point we would have a better handle on some of the safety concerns that are out there, and we have made great progress. When I first started testing batteries back in the early 2000s, they were not nearly as safe as they are now, and so. I don't want to leave anyone with the impression that the lithium-ion battery hasn't made great strides in safety, but we still think that there is plenty of room to go. And really, the largest challenge we have out there is this thermal runaway. And it's even more important to think about this as batteries proliferate and are in the marketplace for even longer because aged batteries have more challenges, we think, than brand new batteries. So aging can progressively increase the safety risks over time, and aging-related failures are very difficult to identify with safety testing. First of all, um, they tend to be quite stochastic. So the number of tests you'd have to do to identify all of the potential age-related failures in a battery system would be quite extensive. And then also aging batteries takes quite a bit of time And we all know that time to market is a premium for OEMs. Um, so if we think about thermal runaway and how it's a critical safety challenge, we define it as an internal chain reaction within the battery cell uh, that is difficult to stop once it's initiated, and it represents a critical safety concern not only with electric vehicles, and the electric vehicles often get a lot of the press when they talk about fire events and thermal runaway, but energy storage system applications also. The panelists before us talked a lot about BESS in data center applications, and obviously thermal runaway in one of those data center applications would be quite concerning. Maybe not necessarily in terms of hazards to life, but definitely hazards to property and in the value lost if a data center was uh, to ever catch fire. And so what we need to do is make sure that the battery management systems um, have very robust monitoring and controls in place, and that the battery system in general complies with the safety standards and the regulatory requirements to make sure we do the best job of keeping people and property safe. So here's just an example of one that kind of illustrates why this is such a concerning event. This is maybe one that made the news quite a bit. We'll play it one more time here. But what you'll see is that this is actually a mild hybrid vehicle that underwent thermal runaway in a house in the United States. And the firefighters were actually inside the garage looking at the vehicle and assessing how to deal with the hazard of the battery undergoing thermal runaway when there was a violent deflagration. And what you saw in that picture was actually the fire chief who was assessing the situation have his helmet knocked off by the garage door that was flying out after the battery caught fire. So it's quite a concerning event. And then as far as ESS goes, we all hear about the problems. The scale of these ESS events can be quite large. In the case of the Moss Landing ESS fire, more than $400 million of written off property, and 1,200 people had to leave their homes. So it was an event that lasted many, many, many days. So there are significant concerns with these battery systems, and we need to do a good job of making sure we assess them for the hazards and that we design them to the standards that'll keep them safe. So while we're talking about standards, we'll just take a quick second to review the applicable codes and standards for BESS installations out there. So when it comes to battery energy storage systems in the United States, the controlling codes are NFPA 68 and 69, which deal with explosion protection and explosion prevention. Um, you know, the only thing worse sometimes with a battery that vents and catches fire is a battery that doesn't catch fire right away, because unless you've got an acceptable explosion prevention system or a good explosion protection system installed in your BESS, you can often have a pretty significant event if those vent gases build up before they ignite. And then overall, we've got NFPA 855, which is the standard for installation of stationary energy storage systems. It deals with the placement and the siting of ESS units. It does require a 9540A testing for lithium-ion battery energy storage systems, which I'll talk about here in a minute. There are some fire and explosion testing requirements, and 855 requires analysis in accordance with NFPA 68 and 69 for these partial volume deflagrations. And then the test method that many of you probably have heard about, UL 9540A, has just come out in the 6th edition. It's got a new proposal in it for a large-scale fire test, which has been demanded by the industry for some time now. And we are working on a new proposal for deflagration testing as an input to the ventilation condition. So, taken all together, this test method and these standards serve as a set of guidelines and rules that attempt to reduce the risk from these battery energy storage systems. On the EV side, again, staying focused on the United States, we've got FMVSS 305A, which is a performance assurance uh, requirement. You have to demonstrate compliance with this requirement, and it mostly deals with in-use and post-crash safety for batteries that are employed in vehicles. So you got to demonstrate the system safety with respect to fire, shock, and gas venting. And it's a firm requirement to sell your car in the United States. UL 2580 is an evaluation and validation standard for batteries. It involves some amount of abuse testing and thermal runaway behavior, but maybe more importantly, with respect to 305A, it also defines BMS limits and controls. And so when you think about these two taken together, we have one standard that basically requires you to demonstrate the safety of your vehicle in use. And then this 2580, which helps define the limits and the controls that are required by the BMS. So, all of these standards very clearly call out this requirement for testing. And testing does a wonderful job of validating reality. But when we think about the limits of testing, there are some limits involved with testing for battery safety. The first thing is that there's a limited scenario coverage. For those of you that have done this testing before, you know that it's quite expensive, both in terms of the cost of the facility and the test itself, but also in terms of the materials that you're testing, especially when it comes to safety testing, which often results in a complete loss of the battery system. So you can usually only cover a limited range of scenarios. Talked about cost constraints, but also time constraints. There's, all kinds of requirements for moving to market more quickly. And so you take that together and you've got some significant resource constraints on the amount of testing you can do. There's also significant measurement limitations. And when we talk about what is involved in safety testing and the amount of instrumentation that you can do and different kinds of measurements that you can put on these batteries, it's often difficult to capture the failure condition perfectly with some of the test instrumentation. And so if you take all of these into account, we're not in the following slides. I'm not going to try to convince you that we can replace testing with simulation, but mainly my goal is to show you how you can supplement or augment safety testing with simulation and some of the advantages of combining the two together. So we'll start off by looking at battery management systems and how simulation can improve safety with BMS. And we start off by thinking that, the first thing we really want to do is make sure we're preventing thermal runaway. And one of the ways to do that is to conduct rigorous testing and validate using that testing a series of models that look at the cell, the module, the unit, and the installation. In particular, when it comes to the battery management system, a closed loop process that can support accurate state of health, state of charge, and other conditions allow us to do predictive monitoring and early risk mitigation across the entire battery life cycle. So we'll take a look here at how we're going to do that. And primarily what we do is we start out with our modeling and testing during the product development process, developing our models and simulating the battery so that we can understand the BMS limits. And then we can use a combination of real-time models and diagnostics to enforce those limits and protect the battery system while it's in use. So the idea is we move from simulation during product development into real-time protection while we're using this battery. So we'll move on here and take a look at a battery energy storage system and how the simulation defines the limits for safe battery operation. Oh. So BMS systems are critical. And as we demand more and more from our battery systems, I think we talked this, there was a few questions on high performance and high power batteries during the panel discussion. We know that we're going to need a next generation BMS to enable safe performance of those high performance battery systems. So we start off with simulation-driven state monitoring, obviously monitoring the state of health and state of charge using a combination of simulation and sensors. We develop the algorithms and parameterization that we then validate using a range of safety tests. And then while the BMS is in operation, we develop and implement simulation enhanced state estimation, which allows a significant improvement in safety and operational reliability. And then we apply that to our BMS. So how do we do that? Well, let's take a look at a monitoring example here. In this example here, we developed physics-based algorithms that use, we say data-driven models, but what I'll say is that they are physics-informed data-driven models that track state of heart, SOC, SOH, and SOP, enabling an accurate lifetime estimation and adaptive BMS limits for safe operation. The example we have here below is developing an algorithm that allows us to model the internal battery behavior so that we can control the charging event to limit the amount of time that the battery spends in the lithium plating region. So these models are integrated into the BMS, and it limits charging, avoiding the overpotential region. And really the key here is to optimize that combination of limiting the amount of lithium plating going on in dendrite formation while also enabling the fastest charge event that we can have. And it's also important to remember that as these batteries age, just like any other piece of equipment, we have to adapt this behavior over the lifetime. So we have to have some way of recognizing the changes in the system and changing our performance predictions as the battery ages, usually based on the state of health. So once we've developed the methods of monitoring these batteries, we can move to developing ways to estimate how they're performing and how their behavior is changing during operation. And we know that the lithium iron phosphate batteries are very popular because they're a little bit safer and have some advantages, but they're also, show some challenges when it comes to estimating some of their conditions, right? Because of some of the flat open circuit voltage challenges in the hysteresis. So if we can develop a tailored SOX model, we can improve the accuracy and enable reliable BMS performance without having to result to extremely extensive sensor architectures. And so we've got some examples here that we show in how we can develop these models to enable more accurate estimations of the battery's state, whether it's charge or health, or even the state of the pack in terms of balancing. And again, I think when we talk about these next generation BMSs where the margin of error is going to be even smaller, and the risk of hazardous events is even higher due to the energy density and the performance nature of these batteries. Um, Accurately estimating the condition that our battery is in is always going to be incredibly important. And then finally, we've got to validate these systems in order to make sure that we're going to have reliable BMS operation. And in this case here, you can see that there's some embedded sensors that kind of work together with this simulation and allow us to have a solid, reliable BMS that has proven accuracy across a wide range of conditions. And it allows us to enforce the safety limits that we've established for this battery system, whether it's a 12-volt lead acid battery like we show here, or a high performance lithium ion battery pack. So, um, as we look at that case study, there's the potential for a lot of benefit from these battery simulation solutions. From a business standpoint, accelerating development, cutting our time to market by simulating performance and aging, and accelerating or reducing the number of tests that we need to take, accelerating our test programs. That also, in turn reduces our costs, minimizing the physical testing and the need for prototyping and potentially a bunch of rework on the design. Also, we think if you have a solidly validated simulation combined with some good physical validation, we can have improved accuracy of the SOX estimates. Taken all together, the improved accuracy and the improved testing, it allows us to optimize the design. And then finally, what we're really after here is enhancing safety, detecting early failures, and allowing us to scale these battery systems into wider applications. So if we think about it, the battery management system has a lot of advantages in real time, can realize a lot of advantages in real time simulation. But there's another use for simulation when it comes to battery systems, and that really comes into play when you're talking about abuse testing. And so if we think about what we want to do with energy storage systems, which often have quite significant safety tests associated with them, especially the ones that are going to be placed inside of dwellings or other buildings where human beings are present. We've got a range of modeling and simulation solutions that are possible out there for energy storage systems. So at the cell level and module and unit level, you perform a significant number of physical tests as you're dialing in the chemistry and the designs of your cells and your modules, looking at a variety of safety factors as well as performance factors. And when we combine that with simulation, we can often get wonderful insights into heat transfer, thermal runaway propagation, and the behavior of the materials in these systems. And then at the installation level, we can look at the development of the system, rapidly iterate using simulation and optimize our design for the fire and explosion hazards. And then finally, we can use simulation in many instances to show compliance with codes and standards. So we think about one of the more challenging applications for battery energy storage systems, and it's fire and explosion simulations. For those of you that work in the simulation area or just on batteries in general, you'll know that simulating fires and explosions are very complex challenges, and there's often a lot of
1341.
maybe
È quello che ne ha di più.
more of a
Però, cioè, sta parlando di thermal runaway, che è la cosa che, no,
Hello?
che noi siamo nella causa del thermal runaway. Lui sta parlando di thermal runaway e intelligenza
Uh,
artificiale, che è chiaro che anche
sir,
io
can
avrei
you
scelto
mute,
lui.
please? Thank you. Okay.
Però ne ha 40, Boris ne ha 30, insomma, tutti gli altri 20, 22, 15, quindi insomma,
Okay. Anyway,
purtroppo non è. Adesso poi
so
a settembre faremo un webinar dove ci siamo solo noi.
so modeling and simulation at the
Sì,
cell and
sì,
module level
devi
can provide some
pagare. A
input to the
Detroit
safety
ce n'è
design
uno, ti costa un botto,
considerations, but at the installation
10.000
level,
euro.
it often can be much more
Paghiamo 20.000 euro il
valuable.
webinar,
We can show that
fidati.
that we're in
Il
compliance with
webinar c'hai
NFPA
500
68 and
persone.
69, but maybe even more importantly, as we talk
Lui è
about
carino,
large-scale
cioè
fire
è un
testing, the
forum,
cost and expense of
c'è
these
ogni
tests,
mese,
along with some of the
c'è sempre
danger that's
250,
involved with
300
them,
persone.
can significantly be reduced when you employ simulations. So let's take a look quickly right here at a use case, one of our use cases.
Vedi, fa vedere le batterie che vanno a
In this case
fuoco,
here,
cioè più
we've
di
got some
così,
explosion
cioè,
testing. This is a standard
vedi,
battery energy storage
se
system.
non attiri qualcuno
And in
così,
this
non so quanto
scenario,
voglio che
we're looking
attiri, eh.
at
Le batterie, questo è
evaluating
come
the
mettere
explosion
una
performance.
bistecca rossa sanguinante davanti a un toro. Dopodiché ci siamo
Hi, this
noi.
is Anna
Bene.
Stefanopoulou. Hi. Terry, can you mute these
I just
people?
did. I'm sorry. I
All right,
couldn't
thank
figure
you.
out how to do it here on Zoom. And
I appreciate it. Thank you.
yeah, it's distracting to everybody. So here we've got one of the explosion simulations that we've done in the past here. And what's interesting about this is that we do pre and post test simulations of these explosions. Um, the pre-test is very useful in that in many cases the code authorities that want to see these results want to make sure that the test that you're doing is often the worst case scenario. But rather than invest a considerable amount of money in multiple tests, oftentimes it's easier to simulate these tests and make sure that the condition that we're running in is really going to be truly the worst case scenario and provide that evidence to those AHJs. Um, we can also take a look at variable parameters and make sure that we put our best foot forward when we're performing these tests. Um, so here's an example of a CFD simulation for NFPA 69. The question that we're trying to answer when we're looking at these kind of simulations is, does the ventilation system or other kind of combustible gas reduction system um, on average keep the concentration of flammable gases below which at the point an explosion can occur. Um, so the strategy here is to prevent an explosion from happening in the event of a venting or some kind of thermal runaway inside your battery energy storage system. It's often quite a robust simulation, and we find that the CFD can do quite a good job of predicting the flammability levels of the gases inside the battery energy storage system, especially if you combine it with some validation tests at the module or rack level. Um, NFPA 68 is a different case. In this case, we assume that an explosion has occurred. And in this case, what we're trying to do is to determine if our explosion safety systems provide enough relief or panel surface area to prevent an overpressure event from damaging the structure and causing even more problems than the deflagration event. And in both cases here, we find that simulation can do a good job of helping manufacturers show either their compliance or estimate what's needed for compliance to these standards. A lot of this is based on modules, and the first thing we want to do is use our simulation work to help us design our modules. And in these cases, you can see that you can very effectively use a simulation to predict how heat is going to transfer among cells in a module and understand what's going to happen in terms of flammable gas concentration as well as heat transfer. And in this case, we do a lot of work with manufacturers looking at materials for these battery packs and battery modules, and it allows us to rapidly iterate on these materials to see what can improve, what can be improved by improving the thermal management in particular of these modules. And then finally, um, there is a requirement to evaluate the thermal exposure from a fire within one BESS to adjacent BESS. And this is key because in many of the significantly dangerous accidents that have occurred out there with battery storage systems, what we see is that it's often very difficult to stop one battery energy storage system from going into thermal runaway. It's just something that sometimes happens with batteries. But what we want to really do is design the system so that that fire does not propagate from battery energy storage system to battery energy storage system and turn a relatively minor event into a major safety incident. And so there is a requirement for these large scale fire tests um, to be performed and generate a report that's provided to the people that are going to permit those battery energy storage systems. And again, when we talk about optimizing the design of your installation, um, doing the design optimization via testing can be prohibitively expensive, and you never really have the chance to investigate all potential configurations. So you often have a significant challenge in proving that your uh, proposed condition is optimized. And so with simulation, not only can we help be more efficient and effective in our testing, but we can evaluate a lot of scenarios and move more quickly to the safe solution. So the power simulation for best safety, hopefully I described it well enough for everyone on the phone. But it really helps you transform a data set into some actionable engineering insights. It does allow us some virtual evaluations out there, in particular for the NFPA 68 and 69 scenarios, and really gives a lot more strength to some of our installation level safety decisions. And finally, just because we're running short on time here, we think that there is a room out there to combine artificial intelligence or AI-enabled simulation with some limited testing to really optimize the design of your battery energy storage system. So this kind of convergence with a physics-informed, data-driven model to improve the design of your system offers, I think, some significant advantages. So now, just as something to be out on the lookout in the future, we've got some significant research initiatives focused on looking at predicting thermal runaway initiation, propagation, and gas behavior using a data-driven model, and the development of some new services supporting this risk-informed safety design. So, wrap it up. The key takeaways here is we think that simulation is a critical bridge between standards testing and real-world battery behavior. There's a, a, a significant number of ways that models can help define the BMS and system level safety limits rather than assume unlimited protection. We can estimate the state of health, the state of charge, and thermal runaway risk, evaluate it together and across the battery cycle. And using simulation and artificial intelligence strengthen our battery safety assurance. I think the key thing, though, that if I leave you with nothing else, I do want to I want to plant the seed and let you know that we do not think that simulation or data-driven AI type methods can replace testing. What they do instead is expand our ability to understand the thorough runaway risk and design our safety margins with confidence. So thank you.